do a little bit of a preamble and draw some pictures for people to set the stage. I was doing this the other day on a Miro, and I thought I would bring it to the call um, so everyone can get some context for why this problem that both Formalized and Karim are trying to solve, and a variety of other people in the ecosystem, is so important for really like the AI industry at large, but for BitTensor specifically. I mean, and that problem is how to train models in a collaborative sense across the wide internet and under incentives. So BitTensor already has a pretty decent set of training mechanisms, 9, 29, 37, 21 subnets that are training machine learning models using incentives. But the difference between the holy grail of distributed training and what we're referring to on this call, the difference is that on subnet 9 and 29, there's no collaboration between miners. Every miner model is a unique team. And with the exception of the occasional model merge that occurs, or like teams that take other models and add layers or add new parameters to the model, there really isn't that much collaboration. And the holy grail is, how do we incentivize compute from across the globe to coordinate together and train a singular model? One that, if I bring an H100 and you bring an H100, Karim, and Formalized brings an H100, we can have three H100s working on the same model rather than each of us training independently. Now, BitTensor has both of these mechanisms running right now. So, Karim, we're going to talk to you about Distry, which has been going for, I think, about a month and had a fair amount of progress and success. And we're obviously going to be jumping into that in a second. We have both of them, and it's great that we have both of these types of mechanisms at play, because we're sort of we're ensuring that no matter what the end result is, we're gonna get something good. So, okay, Mars came a bit late and just started recording, so unfortunately he just missed the whole spiel about the importance of distributed training. But I'm gonna go ahead and kind of draw it out for people on my screen for why this problem is so important, and how we're going to approach it. So y'all can see my screen. You're looking at my Miro. Thumbs up from you, Karim. All right. And make sure people can see my mouse. Yep. Let's go through some components here. Just keep on telling me that you can see what I'm looking at, right?
Yeah, you can see it
cool.
here.
Right, so here's my nice, beautiful drawing of the BitTensor blockchain progressing beautifully through time. No halts, no downtime. Never a hotfix required. And we have here 3 subnets with their incentive landscapes. I think this is subnet 4. And then inside of these subnets, obviously we have miners and validators, and they're setting weights and setting the incentive mechanism. And this is, BitTensor's extremely abstract design for building a variety of different types of mechanisms. Now, the distributed training problem, why is it so important? And why is it the holy grail? There's only X, Meta, OpenAI, NVIDIA, that individually have the GPU power, or prowess, you might even argue, to train foundation models, the things that underpin, Chat and Claude, to the size that is required to get the type of intelligence out to the world that people really appreciate. So like Claude and GPT-4, these are foundation models in the, hundreds of billions of parameters. And subnet 9 and 29 are pushing the limits of what's possible with their training mechanisms. But there's no coordination between those miners. There's no coordination between the compute. And the holy grail of distributed training, it's actually a problem I've been focusing on for, the tensor might have been even invented in my mind to solve this problem. How do we coordinate the compute to train one model collectively and have that model rival in size from a foundation size, a language model that's 100 billion, 200 billion, 300 billion, 400 billion, gosh, trillion parameters training for months. So a bit of a side. So let's take through let's go through like the steps of producing a model that you use for ChatGPT. So there's two steps: effectively pre-training and fine-tuning. We're not going to talk about fine-tuning. It's actually a less of a computational problem. It's more of a skill issue, fine-tuning, about collecting data for RLHF, doing reinforcement learning, coalescing the model that we're going to first pre-train. And in order to pre-train a very large language model, we basically take an infinite corpus of unlabeled text that comes from the web, usually from Reddit, from Facebook, from Twitter, from the common crawl, terabytes and terabytes, thousands of, well, trillions of tokens. And we compress it into the weights of a language model. Llama did this recently with their 405 billion parameter model, which they released, their 70 billion parameter model that they released. And they used 16 trillion tokens. That's multiple terabytes of data. And they had to compress all of that into the parameters of that model over weeks and months of training, depending on the size. And they use a lot of compute to do it. And the training mechanism is actually very simple. Pre-training is like the simplest training mechanism because effectively all you're doing is it's self-supervised. You take a sequence of text and you feed it through your model and you try to predict the next token, and you use the next token prediction logic probabilities and cross entropy to back propagate through your model and update the weights slowly, iteration after iteration, until you converge on the ability to basically predict your data. I like compression as a good explanation for what this is doing. The 405 billion parameter model has remembered all of the information in the web that it's got from its its incredibly large data set. And this process takes months and a lot of coordination. So I want to show you guys this image right here. So this is maybe like, these are H100 pods. I've drawn my H100 pods. This is 1, 2, 3, 4, 5, 6. I think it's about 32 H100 pods. I'm gonna do the math here. It's like 256 H100s. So Meta trained on 16,000 H100s, which is 62 times the size of this. So if you can imagine a cluster of H100 pods 62 times larger than what I'm showing you on the screen. I did actually draw it out once, all 16,000 H100s on a Miro board, but it crashed Miro, and I thought that would be bad for this presentation. So I've just gone ahead and drawn this, which is, as I said, this is 256. So in order to train a 405 billion parameter model on 256, not even 16,000, 256 H100s, each one of them needs to pull from the data set. They need to distribute their 405 billion parameter model across the H100s. So they don't just run it on one H100, they actually split it 8 ways. Indeed, in Meta's paper, they split their 405 billion parameter model across multiple nodes, where the 405 billion parameter model, when you did a forward pass, it was literally running in pipeline parallel. So it wasn't just pipeline parallel, it was context parallel, tensor parallel, and data parallel training. So the 405 billion parameter model was running across many of these nodes. And then when it did a forward pass and a backward pass a number of times, the batch size that it was required to produce an update, it would communicate an all reduce operation with all the other nodes in the network and run an update. Now, it just seems like simple math for people to understand, like the real size of this problem. So a 405 billion parameter model is like at least 100 gigabytes. And if you have 256 H100s in here, this is about 1, 2, 3, 4, 1, 2, 3 by 3. It's about 9. Let's say there was 9 replicas, and then times 64, right? That's 576 nodes that would need to communicate 100 gigabytes of data in order to update their model every step. We can do the math here. 576 times 100 gigabytes. It's 57,000 gigabytes of data, or 57 terabytes of bandwidth requirement in order to do a single gradient step of the entire model and update all of the parameters. Now, in practice, if you read the Lemma paper, it's an absolute masterpiece in engineering. You'll understand that they do have a lot of tricks in there, that they don't need to communicate all of the parameters with everybody at every step, and they're doing compression. They're not actually sending over the wire the float 32 parameters. They're doing compressions down to you even maybe 1 bit compression to communicate the gradients. But at the end of the day, it's a gargantuan problem. It's a very difficult engineering problem just to coordinate this amount of compute and have the bandwidth and compute requirements and the data requirements to train a model that is significant enough to be at the top of leaderboards, rivaling GPT for any reasonable benchmark. So I mean, holy shit, it's a mouthful. I recommend formalize. Could you do me a favor? Actually, find that paper for me and post it into the channel. The Llama 3 paper that the one I'm referring to.
Yeah,
Formalize.
yeah, I'm getting it up.
Okay, great.
Heard of llamas.
Yeah, great, very huge. All right, well, the holy grail of distributed training is, well, hey, what if I had an H100 and you have an H100, and we could all coordinate and work together and combine our H100s and somehow train a model like this without requiring llamas, government scale, Manhattan project scale compute cluster that only a couple companies in the world have available to them. What if we could do this in a collaborative sense? Better yet, what if we could do this in an incentivized way? And I think this is the clutch piece that a number of people have been missing for a very long time. I've been talking about this for a very long time, and I worked closely with the HiveMind team in 2019, and I told them, guys, we need incentives. And why do we need incentives to make this kind of thing work if we're going to try to coordinate a bunch of people to work together? It's just that this is very expensive. 256 H100s, guys, that's like tens of millions of dollars per month. And not only that, but if you want to coordinate these people, what we've learned at BitTensor is that one of the best ways to do that is to craft the problem as an incentive problem. Different things arise. You can guarantee them, if you can craft the incentives properly, you can guarantee that the miners are bringing the right type of compute, because that's the way in which the incentives are aligned. Hey, you can't run from a 4090 on your desktop computer. You actually need an H100 box, and we've seen that across a number of subnets on BitTensor. We can't force the miners to get very sophisticated and to bring a lot of hardware. You cannot do this with altruistic computing. You need some form of incentivization to really scale, and that's something that BitTensor has in spades, right? We have the technology. We have the technology to build this out. But the question remains, how do you even do this? Especially over wide internet, where there's many participants not in the same data center. They could be in different continents across the globe, sharing gradients, 100 gigabyte size, with wide internet connections. A lot of work needs to go into how to reduce bandwidth. And so a couple of weeks ago, I was on a call with Macrocosmos. We were talking about this problem. We were talking about different kinds of compression methods. And there are a variety of different approaches from the open source community. One just came out today called Photon, about reducing the bandwidth considerations. And a lot of those techniques rely on the idea of either allowing the models that are distributed across the internet to train locally do a lot of local steps on their model before they communicate gradients, or to communicate less information per step. So do a compression of the model and only communicate this compression. So there are a number of methods. DLoco, Cocktail SGD is famous. Distro is proprietary; it's under NDA, but I believe we know what they're doing, and all of those can work inside of BitTensor. But in order to make it work, we need to craft them differently. They're all built for kind of this idea that comes out of the research community, the academic community, that money should not be involved, and the academics don't like economics, and they don't like this idea of competition or adversarial behavior. But that's, hey, we were born in the darkness. We know these things as primaries. So we've taken, and by we, I actually am referring to Karim on stage and Formalized on stage, some of these methods that are all about compression, and crafted them in such a way that we can frame this decentralized trading problem as an economic market that can work on top of BitTensor. So without further ado, hopefully that was a good preamble, and if there's questions, people can ask them in the chat. I can see if I can answer them. Without further ado, let's talk to Karim and Formalized about how we're doing this. Great, guys.
Hello, amazing. I'm not sure. Maybe I can. Maybe a good the sort of setup you gave me consists to share a bit about how we're doing it on subnet 38, and then I can hand over to Formalized how he's tackling it himself.
I think that's perfect. Yeah. Give us a breakdown of how it's working on 38.
Yeah. Let me share my screen. Can you see my screen? Okay.
Some blue boxes are rotating, so not quite yet. Strangely not, Karim.
Okay. Let me try sharing my whole screen.
Yeah, give it a go. I don't think he's speaking. People can see it. People can see it. That's great.
Nice, cool. Okay. Yeah, keep letting me know, Const, if it ever stops or anything. But yeah, I mean, I think great.
I actually cannot see it, but others can, so that's odd. Yeah, okay. A lot of people cannot see it. That's strange. Are you sharing slides, Karim? Because what you can do is you can actually just if you're sharing slides, just put the slides into the chat.
Let me do that.
Yeah, just do screenshots and throw them in, or actually just do screenshots and throw them in. That too, and then you can talk over them.
Yeah, I'll do that. I can see a number of people looking at it, but I'll also.
Yeah, I'm in it. All right, Karim, we're good. Let's go.
Cool. Let's go. So the way, I mean, I guess very good intro, Const. So I think the way we're tackling it at subnet 38 is mostly focusing on the first part you mentioned there, Const, which is delaying how often we have to share this huge model size. And so the way we do it at subnet 38, thanks to BitTensor's great subnet mechanism, is we have just two simple signups calls. The first is a train signups call where a validator sends a random layer, chooses a random layer of the model and sends that to the miner. The miner has a local version of the model that it trains on, and it picks a random subset of a global data set, and it trains on that subset of the data. It then sends back the gradient for that random layer that the validator asked for, as well as the subset of the data it trained on. And the validator retrains on that data set and compares the gradient it's calculated locally versus the gradient of the miner. But because we're only picking a very small layer and a very small part of the model, it doesn't have to redo the entire amount of the work. It just does a small subset of it. And so this is a way for it to kind of validate that the miner is doing and training as it is claiming to be training. And then it keeps a global unified track of how many data points, how many gradients all these miners are training on. And it then waits until we hit like a global batch size. For us, we use a very large global batch size, and that's we're able to delay how often we have to sort of average gradients or all reduce, because we use an optimizer called LAM that enables us to not just use like 256 and 512 batch sizes, but batch sizes up to 64,000. And so we're training as every node typically does in a normal environment. And this very expensive, time-consuming all-reduce operation only happens every 64,000 steps. So once we hit those 64,000 steps, we send a different type of synapse call, and that's an all-reduce synapse call. And I think we can maybe go into what all-reduce, how all butterfly all-reduce actually works. But I guess for the purposes of, for people who don't want to dive too much in the technicalities, effectively what all-reduce is doing is imagine every single miner has trained using the same model and gathered a number of gradients. All-reduce is effectively an averaging operation. So Consta's miner averages with mine, with Formalized, with everyone else there, so that we all have a single unified average of those gradients. And once that's the case, we then apply those averages to our model and update the weights using the same optimizer to get to the new model step. And effectively, we've just gone through one iteration or one step or one update of the model. Now our validator sends this synapse call and gets all the miners and joins the miners in running an all reduce. And through running the all reduce can tell which miners have succeeded and failed in this averaging operation and penalizes them accordingly. Now, as Cons mentioned, all reduce is very highly dependent on bandwidth. And so we also have a proxy method for evaluating bandwidth by asking miners after they've done the all reduce to stream parts of their model and timing how long it takes for them to stream their model to get a proxy metric of their bandwidth, which is highly correlated with whether they'll succeed or not with this all reduce. And once this all reduce operation terminates, the validator has everything anyone's validator will upload that model to Hugging Face so that any miner that's failed can pull it back down, or any new miner that's joining at this step can pull it back in. And then we go through the loop over and over again. We train, we hit the batch size, we all reduce. Anyone who fails reloads the model, and we go over and over again. Now, this is a good system for small model sizes, but needs to be tweaked as we grow. But so far in the last 30 to 40 days on the subnet, we've done pretty well training on 250 million, 500 million, and I think live now on this Hugging Face dashboard, you can see we're training on a 1 billion parameter model. And if I zoom in a bit here, what's happening here is this is kind of like the baseline run of what would happen in terms of your model's loss if you were just training this model on your own, if you got a couple of H100s or just trained on one, but on the same batch sizes. And here in blue, you can see how our collective 250 miners are training on a single model. So we're performing quite close. Granted, it's a bit slow, but a bit close. Sure. You can't see my screen. Let me share the. Yeah,
I've already done it.
Cool. And here's the link if you want to look at the actual live model. I'll go back to the slides. And so that's effectively how we've been progressing with this problem. And I'd like to say pretty well with a 1 billion parameter model that's been training and converging pretty nicely. And that probably maybe a good leaping off point to talking about this with constant distributed is this final slide here that talks about kind of what we are aiming for in our subnet. And that's like maybe a good way to visualize the strength of a distributed training system is through this pyramid. Maybe pyramid's the wrong analogy. Maybe you can think of them as 4 loops integrated. But effectively, what we care about with distributed training is sort of like a number of things. The first is the model size, and that's what we've been steadily increasing. If you're doing great and you're proving people are training, but you're only training on like 100 million parameters, 500, it's not that effective. We want to be growing quickly, and we want to be rivaling these big models that can be state of the art. And so, as I mentioned, we've jumped from like 250 to 500 to 1 billion. And we're hoping over the next couple of weeks, months, to be pushing the frontier of what you can, of the model to the maximum size model you can have on a single GPU. So depending on how clever you get, we're talking 7 billion parameter model here. But once you're scaling the model size, the important thing is also how well you're converging. So can you bring the model's loss down from the likes of what we were seeing on the graph there of like the 10.8 to the 10.9 loss you're starting with, down to low losses, low reliable losses, to effectively prove that you're training and that people aren't just feeding you garbage gradients. And then the third layer on top of that is how quickly you're training. So let's say you're upping your model sizes, you're converging pretty nicely. You also want to make sure you're not taking hours and hours and days and days and days to train. And at the moment, it's taken us 30 minutes to hit this global batch size of like 64,000 gradients, and about 5 minutes to average them. And as we grow our model size, obviously this becomes more of a challenge because you're averaging bigger data, but we hope to keep our benchmark close to that and even reduce it a bit more. And the final cherry on top is like how decentralized you are, but this is, I believe, a nice to have at the moment. We've currently sacrificed a bit of decentralization for stable performance, and so we have one UID, master UID, that controls when we run this averaging operation. But we can easily see a world in the future, as the system gets more stable, that we have more UIDs that are capable of triggering this all reduce, and even potentially miners in the future. So this is just like I guess, a brief summary of where we were with, or where we're going with Subnet 38. Not sure if anyone has any questions, or maybe Formalized. I can hand over to Formalized as well.
So I want to say something though, Karim, because it might not seem that interesting to some that we're only training here a 500 million parameter model, but this
1
quite
billion.
literally, this 1 billion, right? But every time that you increase the size of this model, it is the largest incentivized decentralized trained model in the world.
Exactly. I mean, I think up until Prime, came up with what is, I don't believe, is a trustless mechanism. Even the state of the art in most papers you look at, I think if you look at, if I'm not mistaken, even distro, we're doing it just on the 1 billion. Maybe I'm mistaken. So I think we're very close there to the state of the art of what people were just doing in a trust-filled environment. So I think that's a good distinction and a good reminder for everyone is, yes, in the normal world, we talk about trillion parameter models, but in the decentralized, distributed world, 1 billion has kind of been the frontier for a while, and we're hoping to move past that very soon.
No, but specifically, Karim, it's not just decentralized. It is incentivized.
Trustless.
It is trustless, it is incentivized, and it is decentralized. And those three things are required. And no team in the world has ever achieved it. As far as I know, I've never heard
trained signups, there's still a ways to go there, but we basically picked it by allowing people, effectively, the way we, part of the reward calculation is based off of how many dataset indices you train on in the period the signups is sent. So effectively the formula here becomes the more compute you can power up into your miners, more data sets. And so there's a high correlation between the miners that are trading the largest amount of data set indices and those with the higher incentive. And effectively, it's a two sides of the coin, and we try and balance it. It's compute and bandwidth. And so the other formalization of the reward score is how fast bandwidth are you providing? How much bandwidth and how much upload and download speed are you providing? And the way we formulate that reward problem is we after you run the all reduce, we load the model state you're loading through an RPC call that's opened up, and we time how quickly you're able to respond to that call and upload your model to our validator abilities, and we fix them. So I think we can sustain an increase, but not like in honest fairness, we want like a tripling size in our emissions. We want a steady, 50% increase, 25% increase. I think we can sustain, and that it's open to obviously debate and to experimentation and finding out as we grow. But we do have plans to improve and sort of strengthen up our validation mechanism. But yeah, as we've touched on, these are all theories as to what's a robust and tight validation mechanism, and we're experimenting as we go. Currently, our theory is with the subset of like 20% of the gradients we're testing, it's quite difficult for people. We assume it's quite difficult for someone to hack their way around training the data, but being able to recreate 20 to 30% of the right gradients. And that remains open to be tested even further.
Beautiful. We have Stefan on the stage.
Hey, I guess first of all, Kareem, congrats. This is a super, super cool design. Congrats on being the first in the world to do this. That's quite an impressive move. Amazing. Also, sorry if I'm a little bit late on catching up with the design here, but so I guess could you break down for me how does the validator actually verify that the gradients are correct? I think you may have just explained a little bit of this, but I'd love to hear a little bit more.
Yeah, sure. So it sends a random layer of the model to the miner, and it asks the miner to send back gradients, a compressed version of the gradients for that layer for each of the dataset indices it's trained on. And it retrains on a subset of the dataset indices the miner is trained on, and it recalculates them locally and compares the difference between both gradients.
What's the comparison method you're using?
At the moment, it's a simple difference in an absolute difference, but we're considering potentially moving to a cosine similarity very soon.
And I
Perfect.
guess,
Go ahead, Steph.
thanks. The follow-up for me is, I guess, what's the sort of ratio of samples the validator would need to train on to get a good estimation of the same gradient that the miner has uploaded? Is it sort of 1-to-1? You're just doing sort of spot checks once in a while, or is it possible for the miner to do a lot more work and train on a lot more samples, and the validator still has some confidence that their reference gradient is correct?
Yeah, exactly. I mean, that's the hyperparameter we keep experimenting with. At the moment, in each synapse call for each miner, we're testing about 10% of what the miner is doing. We found that, I mean, through testing on testnet to be a sort of very, very fine line, but it's a hyperparameter we constantly tweak. At the moment, 10% feels right in our analysis of what we're trying to see versus what miners are actually doing. And it's a hyperparameter we keep tweaking.
That is super cool. I know Jake has been scratching his head about this for a while, and we've had sort of a collegiate debate, you might say, about how much you can offload to the miners about this. But it sounds like 10% is a sweet spot right now. So congrats, guys.
Thank you. Yeah, it's an ongoing problem. I mean, I guess in a ways it could be incentivizing miners to try and be able to predict like these gradients well, but in a sense, I'm not sure to what extent like them being like there's a maybe a hack, but the hack is this probably the same compute intensive as just actually training on the data. So it remains to be tested and monitored and seen, and I think it's going to be an ongoing, unfolding problem to try and solve.
The accuracy here of the validation design is where all of the, in my mind, the gains can be made, because if we're just measuring raw compute and not something more in the direction of improving the model, we do limit the ability for the network to actually surprise us with improving. So one of the nice things about subnet 9, obviously, right, is that we don't care how you train your model. We just care about the loss. And so the hyper focus, I believe that there is an outcome here where both these subnets actually sort of pale in comparison with improvements on 9 and 29, where the system gets better at allowing the miners to coordinate together or collaborate. We're sort of approaching the problem from different sides, right? So on the distributed side, it's like, hey, we're going to force collaboration, and then figure out incentives that will make the collaboration work. Whereas on 9, there's no forced collaboration, but I know that on your team, Stefan, you guys are trying to figure out ways to allow different types of model merging to occur, and so we could actually see a kind of convergence between the running of the two types of networks.
Yeah, absolutely, Jake. We were pleasantly surprised and a little bit shocked when we looked at some of the models that the miners had uploaded on Subnet 9 and found that they've been very creative. They've figured out ways to take 7 billion parameter models and make them walk and talk like 14 billion parameter models. It's all quite genius. And I think the thing I'd highlight there is this is like a very, very early field in sort of pre-training, finding out how you can use a smaller pre-trained model and inflate it to look larger. I think it's a big engineering challenge, and the miners are the ones, fortunately, that are left to figure it out.
We have Autometa on the stage. Nice to meet you, Autometa. I know that you were brought here by Distributed. Welcome to the stage. Hopefully your mic works.
Can you hear me?
Yeah, we can.
It does work. Yeah, I have no idea what's going on. I clicked on a whim, and then the coolest conversation I ever heard was going on, and so now I'm on stage.
Well, great. So we have Karim Subnet. He's like Christopher Columbus for incentivized decentralized machine learning. And we also have Templar that launched, formalized here, heading that, which took the Kant design that we were working on for a while, that I was working on for a while, and has made it into a reality, and is running on Subnet 3 now. And when I was speaking to Karim recently, I was like, hey, we don't know if the field's going to go kind of like model slicing or lots of local steps like deloco. And I think that, we do need experimentation to occur. And so maybe this would be great to have Distributed talk about, Templar and the run that you currently have going there. Samuel, do you want to
Okay, so it's pretty interesting, as there's different ways to solve the problem, and we've decided to go with the very iteration that we can take a subset, we can have miners train on deterministic subsets of the data and broadcast this across the network, and have the validators and have the validators. It's almost kind of like what the aid does, where they reevaluate, because it's deterministic within that within that window. They can evaluate that miner's contributions and do a cosine similarity around it. and get a similarity score. Now it's really interesting because we just started writing it. Then we still have some research going on that is kind of pointing at that there's a certain sweet spot for compression that leads to better convergence. So what does this mean? Is that it's a multifaceted beast, and there's loads of things to optimize for. And we wanted to constrain the surface area of our problem to just how well can you train? So in this subject, it's about, for a miner, given your page, how well can you reduce the loss? So we fixed that by we don't do peer-to-peer because I've worked in blockchains for ages, and peer-to-peer is peer-to-peer networking is another tail-ended beast that's not very performant, and we just didn't want to attack that. So by virtue of using S3 buckets, we offload all that. We offload a lot of the checkpointing, and we can just focus on, look, as a miner, what have you done? So we're measuring their share contribution towards reducing the loss. And so far, the current run, we seem to converge pretty quickly. But again, we just started. The incentives are not high, and the real tricksters from the ecosystem are not here. I'm not here yet, but it's looking really promising. It's still early days. Now, what we like about these about reason.
Wait, Samuel. So what are we looking at here? So just give some context. Yeah.
So this is a validator's loss after about 120 steps.
It looks like you need to make the run public. Formalize.
Okay, I will do. I'll do that shortly after. But yeah, this is, and we still need to sort out getting all the validators on 1DB so we can see how they all converge. But this is just after about 120 steps. A step for us right now is about 20 something seconds. So, by focusing by just reducing the problem to how well can we train in a distributed setting, we don't care about bandwidth, we fix that. All we ask for is your raw compute. Now, there's some interesting limitations here, and it's a different kind of optimization problem because it being a global model, things like optimizer states and we don't average optimizer states, but by virtue of the validator mechanism, it's fixed. So we just exposed to the miner is, okay, this is the system. You can't change the optimizer. Can you figure out how to drive this loss as low as possible? And so in the beginning, we can expect that everyone runs the base miner and throws more compute to it. But there's so much alpha in being able to understand the model architecture, which layers to train, and probably figure that out because I trust they're very give incentives and the miners will come. Now, another interesting part of our run is that most optimizers are bound with learning rate schedulers. They're bound with you need to have a priori knowledge of how many tokens you want to run and how many tokens you want to run and how long your batch size and your token step. But we're using a WSD learning rate scheduler. So what this means is that we can train forever. But so in a WSD scheduler, you get a warm-up phase, then you get a stable phase where you train at a high learning rate, then you get a decay phase. But you can run this training phase forever. But once you start to decay, that training run is kind of over. But what we're doing to lend itself to BitTensor is that we're on a 1.2 billion now, just to warm things up. We can keep training that 1.2 billion model. Then every week, the team will just run the decay steps and post an eval. So even for given the setup, not only is it